Imagine if the next industrial revolution came about on the backs of Scotch tape and pencil lead. If it seems far-fetched, well, this is the least of it. Graphene was discovered by Dutch-British physicist André Geim and his colleague Kostya Novoselov. They were trying to make graphite as thin as possible, so they used Scotch tape to peel a sample apart layer by layer, until they were left with a substance 1 atom thick. But that's just the tip of the iceberg. Graphene is made of 0.142 nanometer long carbon bonds. It's just the carbon doesn't have to lose strength by bonding between layers. That makes graphene the strongest material we've ever discovered. Graphenia.com reports that graphene has an ultimate tensile strength of 130 billion pascals, or 130 gigapascals. For comparison, structural steel is 400 million pascals strong. Graphene is also incredibly lightweight, with 1 square meter being approximately 1,000 times lighter than paper. In fact, it's been said that a single sheet of graphene large enough to cover a football field would only be about a gram. But not only is graphene super strong, it's also super conductive. When carbon atoms bond to create graphite, 1 electron is left unpaired. If an electric current is applied, those unpaired electrons will rocket across the network of atoms. However, since graphite is made of layers, the electrons have a lot of places to branch off to, decreasing conduction. But strip graphite down to a single layer, graphene, and now the electrons have a 2-dimensional matrix of atoms to play on, so no conductivity is lost. Graphene is also an incredible conductor of heat, averaging between 2,000 to 4,000 watts per inverse meter Kelvin at room temperature. For contrast, diamond measures in at about 2,200 watts per inverse meter Kelvin. All this means is graphene can very effectively move heat across large areas. But how do we get this amazing material? Well, you can always try the Geim-Novoselov method and cut a piece of graphite in half until we get a layer 1 atom thick. But how many times will we need to cut it in half to get our graphene? Let's take a piece of graphite that's, say, 1 millimeter thick. Going back to Graphenia.com, they list graphene as 0.345 nanometers thick. Now, with this data, we can create an exponential function that should give us our answer. To start, let's get common units. A millimeter is 1/1000th of a meter, and a nanometer is 3.45 times 10 to the negative 9th meters thick. So right now, our equation looks like this. Let's get rid of the millimeters and log base 1/2 to get rid of the exponent. That means, in our hypothetical scenario, it would take about 18.14 cuts to get us to our graphene. Now, talking about how great graphene is all well and good, but what can it be used for? For one thing, I'm willing to bet whatever you're watching this on right now has a battery that infuriates you, with its short lifespan and long recharge time. Taking advantage of graphene's superconductivity, lightweight, and flexibility, batteries could last longer and be lighter than ever. This might not mean much on a phone, but on a plane, it means the world. Speaking of the world, we're a little pressed for energy, aren't we? Well, with graphene, it's certainly possible to use long cables to bring heat from beneath the Earth's surface up to us without losing any energy. But we're not done messing with the planet yet. All that water we can't drink won't stay that way for too long if we take porous sheets of graphene that would allow only small molecules to pass through and use them in desalinization. So, I'm sure you're wondering, if graphene is so great, then why don't we have all these amazing things? Well, graphene is really hard to produce. It's a very uphill battle. Cutting a sheet of graphite in half on a large scale isn't really practical. However, there are a lot of people out there looking for a way to make all these amazing possibilities a reality. For example, MIT has been developing a way to grow graphene on sheets of glass. Normally this process would be done on a sheet of nickel or copper, and then transferred off to a substrate, but this process can lead to contamination of the sample. The new method still uses a metal film as a template, but instead of making graphene only on top of the metal film, it makes graphene on both the film's top and bottom. The substrate they use is silicon dioxide, a form of glass, with a film of nickel on top of it. Then, using chemical vapor deposition to deposit a graphene layer on top of the nickel film, the team were able to produce graphene on both the top and bottom of the sheet. The nickel film can then be peeled away, leaving just the graphene on top of the non-metallic substrate. This way, there's no need for a separate process to attach the graphene to the intended substrate. And the substrate could be anything from a large plate of glass for a display screen to a thin, flexible material that can be used in those incredible batteries we talked about earlier. So, while fantastical graphene technology may lie just outside our reach, like everything else fantastical, we're well on our way to reaching it.